Actually, what I have to show here are a presentation of a group of structures and models that feature 11 and parallels, which were criteria. Here is a glass structure that's composed of 11 left-handed and 11 right-handed, two sets. If you have something that it's double-handed, it's left-handed and right-handed, and when you compose a structure that way, it has the kind of chirality that if you hold it in a mirror, the image is a duplicate of itself. The next item is a related structure, which is actually a stack, a double of this 11-fold rotational group. The 11-fold rotational thing is sort of like folded hands from a species where they had 11 fingers and no opposable thumbs. Right hand, left hand. So this is a double of it. It's a stack that you kind of can construct this as a kind of a column where the center. So the advantage of doing this is that these are now bundles of four wires in a bundle, and that has a cross section so that when you construct it this way and you draw the ends of the bundle together, it forms a stable equilibrium. Stable equilibrium where the center lines of the bundles meet at a common point center. It therefore physically defines an 11-directional intersection, a coordinate section system where there's an origin point at the center of this and 11 lines. It's not very science fiction-y. It's kind of more down to earth. This is not hyperspace. So once you have, maybe it would look better if I hold it up like that. Once you have that, then you have a choice of how, if you want to proceed and try and construct polyhedra, you can go parallel with any of these and form rhombuses. And by following that rule, is if you say you're only going to use, you can say that you're only going to use unit lengths and sort of filter out all the possibilities. If there's one of these, and any one of these can be considered a branch point if you go out X distance, a plethora of possibilities of how these things might go from there. But if you say that you're going to make a convex polyhedron where you start from this origin point and proceed with these isometrically using unit lengths, and you can then generate this 110-hedron, say. And it's has a kind of a kinship or resemblance, say, to pineapple. So then the next thing that you have to consider is if you've done that and you've come to basically a node at the top, if you started at the bottom, and kind of adopting the convention of, say, coordinate locations that we use in X, Y, Z, you'd go at 1, 1, 1, 1, 1, 1, 1, up to 11, and then you're back to a node. So at that point, you can introduce a second length. And this is kind of the subject of modulation, where you can now adjust to a different length, a second length, introduce a second length. it's what I call nodal modulation. There's also this band around between those polyhedra. So if you look at that, it's like strings of beads, a chain. And this is everything in between it. There are ways of configuring kind of sub-cells that you can do symmetrically all the way around. I just have this one segment. The idea of modulating, by which I mean if you take a cube, for example, and if you stretch it and compress it, it becomes more of a brick shape. So in this circumstance, you have a variety of options, a large variety of options, where you can start with a unit length and progress around with a variety of other lengths. In this case, it's done with a plane of symmetry. So there's one length, and then there's two others. So there are 5 pairs plus 1. So this is a modulated cell of this. I'm going to rush. Which, if you just look at the top, the polar cap, it has this curious resemblance to a palmate leaf structure. All right, I'm going to hand it over to Jane. One more thing. This is a combination of a 5-axis star and a 6-axis star. There's a set of holes through the 6-axis star that just fit a 5-axis star. 11. Thank you.
This 5-axis is completely analogous to what John was describing in 11, but a little simpler because there's so many fewer. This is a wooden version of the same object. I don't know whether these see better on here or here, but we wrote down Quintetra blocks as what would be. It came out as what we'd be speaking about. I actually had intended that as what we submitted to the paper, and you'll all get a copy of. But I'll talk about it briefly and show you models. So I'm just going to pull out some wooden objects. This is a set of. This comes from a completely different set of lattice structure, octet actually. I can describe it more for those who are interested. But this block here is a very unusual shape. I made a bigger one. Maybe it's more visible. You got all kinds of crazy angles, 113.86, 66.14, 65.91. If you turn this on, that's actually something you can cut out of paper and make your own, and I've given a PDF file that anyone can get. It shows where some of those angles come from. But so this block, we can go back to this this Elmo thing. 30 of them completely surround a hollow center, although in this case it's not hollow. I put something in there that relates back to the most familiar, which is 3-axis. This here is pretty familiar. Those sets of directions like that. Now, in this case, inside is a tetrahedron. There's 5 sets of, you can make 5 sets of cubic systems all together. Here's 5 cubes that are, you can see how the metal wire is a pentagonal dodecahedron. So you can see how each cubic system relates to a dodecahedron. But now if you build all 5 of those at once and just keep building outward, you end up, this thing, I've got another one of them built in colors where I took a block and I made it out of 2 kinds of wood. So I'm off the screen there. So that you get 2 colors per. Now black shows up nicely, so I'm going to stick a finger in the black. There's another. There's another. There's another. That's a tetrahedron. So there's 5 such ones. Now, I could take this thing all the way apart, and if you enjoy putting this kind of stuff together, you can meet me later and play. Now, John, getting back to John's concept of modulation, you can do the same thing on this object, but what gets real interesting, and I'm going to show you this, where I took one of them and I skinnied it down. If you can go back to this thing, I drew a line following each of those tetrahedral 5 choices. And then here's a set where you skinny down the yellow one, the path the yellow's on, and then you eliminate it completely. You can eliminate them so you can modulate each and any one independently of the other. Anyway, in finale, let's go back to this one. This one breaks down into yet another. So that was the triicontohedron built out of 3 axes. This shape, triangles and squares. And then you're down in the middle to a rhombic dodecahedron. So this is, gives you a little taste of what we do. I'll open up so you can see what's going on inside of the 5 axis. Like that. And then, of course, those are all. This will be my finale of destruction. It opens up some way. Okay. So anyway, meet me afterwards if you want to put all this back together.